Why some things explode, but others don't? It's like there is something that decides what happens and what doesn't. This is Gibbs Free Energy. This simple equation saved billions to the industry. But why then, one of the most powerful equations in all sciences, it's always explained so badly? Let's change that, shall we? Imagine this. You don't know electricity exists. This extraordinary technological system, it's still only for the rich. And this is your phone. You studied mechanical engineering and mathematics at Yale University, so you know that energy is being transferred throughout a reaction. But you want more. You want to know why things happen while others don't. You want to be able to predict the outcome without even making your hands dirty. Your name is Josiah Willard Gibbs. It's 1876 and you just published this paper. Over 300 pages of dense mathematics. Respect. You showed that if we can predict where the energy flows, we can predict the outcomes of any reaction. How did you do that? Well, you took the two most fundamental quantities in thermodynamics, enthalpy and entropy. You had a temperature and combined them in this equation. If your equation actually works, it would predict that an ice cube on the beach would melt. If it doesn't work, it will predict that water freezes on the beach in summer. What you know is that there are two ways to exchange energy: heat and work. When you heat something, molecules are not moving in any specific direction. It's complete chaos. So heat is a messy way of transferring energy. Just to be clear, what we mean when we say heat, we mean energy transferred through a random molecular motion, while work is energy transferred through the same direction. So the atoms move all together in the same direction. It's like a piston or when your hand gets smashed. Okay, now we know how energy is transferred, but how do we agree on the direction? We can use a sign to indicate the direction of the energy flow. If energy flows into the system, we use a plus and we call the reaction endothermic. If energy flows out of the system, we put a minus and we say the reaction is exothermic. One of the most important energies is the total amount of energy exchanged. And since the total amount of energy transferred is actually heat, no, it's not. What do you mean it's not? It's heat only at constant pressure. Okay, so we need to name it after something else. No, we can name it after heat. What's the Greek word for heat? Thalpos? Okay, let's call it enthalpy. But remember, enthalpy is the total amount of energy exchanged. It's not just heat, okay? It's heat only at constant pressure. And since we can only measure exchanges of energy, we write ΔH, so enthalpy change. So in a mathematical language, we say this is a state function because we only care about the energy is at the beginning and at the end. We do not care where the energy went throughout the whole process. Now bear with me. Enthalpy is the total amount of energy exchanged. Out of this energy, a small amount is used to transform the structure. So we can pass from a more restrained structure like the ice to a more freer one, like water. So the molecules in the ice can move less, and in this case we say the ice has less microstates. While in the water, molecules can move more freer, so we say water has more microstates. So when ice melts, the molecules in the ice absorb the energy from the molecules moving in the air and transform the structure. So how much the system loses energy to have more ways of movement depends on the average energy of the particles, temperature. Hence, the energy used to transform the structure is enthalpy change over temperature. Since it's energy involved in a transformation, we can use Greek word tropy, which stands for transformation. And thus we call this energy entropy. So entropy tells us how much of the total energy exchange goes only into transforming the structure. Now let's take the water vapor transformation. So water absorbs energy from the molecules moving in the air. These molecules, they keep absorbing the energy, vibrate more, they bump into each other more. We can divide the total amount of energy into the energy used to transform the structure and the energy to move faster. And this energy that is used by the molecules to move faster is the only energy that we can actually use to do work. And we are gonna call this energy Gibbs energy. So the energy that we can actually use to move stuff will always be less than the total amount of energy exchanged. So a super summary would be: enthalpy change is what you put in, entropy change is what is stolen, and Gibbs energy change is what you end up having. It's like enthalpy change is your gross salary, entropy change is the taxes you have to pay, and Gibbs energy change is your actually net salary. Now we can use the Gibbs energy change to actually predict if a reaction will happen spontaneously. And we can see different scenarios. In this case, nothing really happens because the total amount of energy exchange is actually equal to the energy that is needed to change the structure. So this is, for example, the case of water at 0 degrees Celsius. In this case, water is actually just as happy to be water as it is to be ice. Push, and the transformation will occur spontaneously. This tells us that we end up having more energy and less freedom of movement compared to when we started. So this reaction will never happen spontaneously, but only with an artificial push. Why? Because everything happens to more stability in the universe. The more stable, the less the energy. Then we tend to maximize even more the stability by spreading out this energy as much as possible. Entropy. What Gibbs tells us is that if we want to make this non-spontaneous reaction to occur, we need to supply this amount of extra energy to compensate for the instability of the new products. It's like you want to transform graphite into diamonds in your room. It's never gonna happen, no matter the temperature you use. If you want to make that transformation to occur, the energy you need to supply is about 60,000 atmosphere of pressure at 1,500 degrees. It's like having 5 buses on your fingertip at 1,500 degrees. Or you can go inside the Earth at a depth of 225 kilometers, and in those conditions, diamonds is actually more stable than graphite. That's why they form there. In this case, we end up having less energy and more ways to move. So not only this reaction can happen at any temperature, but we actually end up having an extra energy that we can use to do work. One example is methane combustion. The products forming from the combustion of methane are more stable and can move more freer than the methane molecules. That's why even if you go at minus 40 degrees, you can still burn methane and warm up. And the warmth that you feel, it's precisely the Gibbs energy. So this is an exothermic reaction, and the molecules will end up having less energy, which is good, but unfortunately will end up having less freedom of movement, which is not good. So this reaction will happen spontaneously only at low temperatures. One example, water freezing. To turn water into ice, water needs to give up energy to the environment. But if in the air the molecules are jiggling way too much, then they cannot really absorb the energy coming from water. To start absorbing that energy, they need to have less energy themselves. So now they can take in the energy that water releases as it freezes, allowing water molecules to slow down and rearrange into solid ice. This is an endothermic reaction, so the system will end up having more energy, which is not good, but will end up having more entropy, so more freedom of movement, which is good. So this reaction will only happen spontaneously at higher temperatures. One example, ice melting. To turn ice into water, the molecules of the ice need to absorb the energy from the molecules of the air. But if the molecules of the air don't have much energy, they're not vibrating much, so we are at low temperature, there is not much energy that the ice can take. If instead the molecules in the air have much more energy, so the temperature is higher, they're jiggling more, they have more energy, so the molecules in the ice will start jiggling so much that they cannot stay in place anymore. So the crystal breaks apart and the solid turns into liquid. So all the enthalpy changes and the entropy changes are fixed by nature. And you can find them in any chart online or in books. Okay, but how the heck did they get enthalpy changes and entropy changes? Did they measure them? Did they calculate them? What do you want? Hello? Hello? I need to finish this video. Can I? We can cut it later. Enthalpy changes are the easiest one. The simplest way to measure it is with a calorimeter. In some cases are also calculated in a very complicated way, but in this video we're gonna just stick to the simplest way. So they put the sample, for example ice, inside an insulated container surrounded by water. Then they take the temperature of the water before starting the experiment, and what happens is that the ice will absorb the energy from the surrounding water, thus lowering the temperature of the water. So we get a temperature change. Then we multiply this for the mass of the ice times the heat capacity of water, which is the energy that water can absorb. And we finally obtain enthalpy, the total energy exchanged. Okay, but how do we know the heat capacity? We also measure it with a calorimeter. Same insulated container, you put an electrical heater inside, you measure the temperature before starting the experiment, then you heat up the water, and then you take the temperature again. So we have a temperature difference. Then you divide the used energy by the temperature difference. But how do we know the energy that we used? This is the cool thing about electric devices. The amount of energy is equal to the voltage times the current times the time. Speaking of electric stuff, let's talk about the Gibbs Free Energy for electrochemistry. In this case, Gibbs energy tells us how much work we can get from a redox reaction. Let me explain. Take your phone for example. So the reaction happening inside the battery of your phone drives an electric current throughout an electric potential, and it moves a big amount of electrons. Now, the electric potential is a concept that I think it's kind of hard to grasp, so I will try to explain it in simple words. I like to make the comparison of the electric potential with gravity. So let's take an apple and drop it. If we measure the force by which the apple hits the ground, we will find that different apples will hit with different forces. If we divide the force by the mass of the corresponding apple, we get the same number, which is the acceleration on Earth. You do it on the moon, and then you get a different number, the acceleration on the moon. And this is very useful because you just then need to know the mass of the object that is falling, and then you can calculate the force backwards. The electric potential is basically the same thing, but just with charges. Now, let's say we have an electric field and we put a charge inside. Of course, this electric field is generated by other charges, but we don't care about those charges for now, okay? So we have an electric field and a charge inside. If we put inside then different charges, we're gonna find out that these charges are gonna feel a different forces for each. Even better, they're gonna feel a different energy. And if we take all the energies and we divide them by the charges, we get all the same number, the electric potential. So it's the same thing as the apple falling, just you can do it in any direction. And this number is crazy useful because we just need to know the amount of charges that is passing on that electric field through that electric potential to actually know how much energy we're gonna get out. Or the other way around, we know how much energy we need to use to actually move those charges inside that electric field, so throughout that electric potential. So it tells us what energy any charge can potentially generate inside an electric field. That's why it's called electric potential. To understand how much energy we can get from this to do work, what we do is multiply the amount of charges you have inside, which we measure it in moles, times the charge that 1 mole of electron has, which is Faraday constant. And then we multiply it by the electric potential. And ta-da! We know how much energy we can get from that battery to do work, like watching this video on your phone, for example. Gibbs energy tells us if a reaction is possible, but the problem is that it doesn't tell us why. To answer to that question, we need to understand something else, and it's called chemical potential. Watch the next video to finally understand the chemical potential. Can I finish? I finish here and then we cuddle as much as you want. Okay? Don't make the face. You make me feel guilty.